For this lesson, we're going to be looking at factoring polynomials. This lesson is really a continuation of the previous lesson, which was on doing division using polynomials or division of polynomials, because a lot of the mechanical skills from the previous lesson are important to this. Now, to start off with, two theorems. Theorems are just a set of statements that have been, they've been shown mathematically. So we have the remainder theorem and the factor theorem. We're going to be making use of these. Really, the factor theorem is just a special case of the remainder theorem. So the remainder theorem tells you that if you have some polynomial represented using function notation, when we talk about dividing by the factor x minus a, the remainder we get is the same thing as taking this value a and plugging it into the function. Now, another thing we talked about is when we were doing long division or doing division, if we divided by this small polynomial and we got a remainder of 0, that meant that this was a factor, meaning no remainder. And that's what the factor theorem says. If you plug in this value of a and the remainder, or the result you get, turns out to be 0, that means that x minus a is a proper factor. It means you're going to be able to write your polynomial in factored form using x minus a. Now, I have an example here, and this example is actually a problem that we solved using long division in the previous lesson. So I'm hoping that some of you will find that familiar. You've seen it before. You might remember this result. And the key thing that I want you to focus on here is that our remainder was equal to 14. That this is, we're dividing by x minus 3, which means that in this case, my a value is equal to positive 3 because it's x minus a. So this is a is equal to 3. And then this piece here, that's my function of x that I'm going to be making use of. So if f of x is this original thing that I was dividing by, so 3x cubed minus 5x squared minus 7x minus 1, and we were dividing by x minus 3, then if I evaluate f of 3, what the remainder theorem tells me is that when I put this value in here, a, my remainder, so this remainder of 14, should be the same result that I get this way. So that's going to be 3 times 3 cubed minus 5 times 3 squared minus 7 times 3 minus 1. So we have 3 cubed, which is 27. So 3 times 27 minus 5 times 3 squared, which is 9, minus 7 times 3. I could have gone ahead and evaluated that. I should have, really. 3 times 27 is 81. 5 times 9 is 45. 7 times 3 is 21 minus 1. And if you go ahead and do your arithmetic here, you might want to do these negatives first. 45, negative 45, negative 66, negative 67. Subtract that, we end up with positive 14, which of course is the remainder I had here. Now the remainder theorem can be useful, but if you wanted to get this full answer, you were still going to have to do your division, long division or synthetic division. But where the remainder theorem becomes really useful to us, or very powerful, very efficient, is the remainder theorem, using the remainder theorem to look for a remainder of 0, which is the factor theorem. That's going to be much more useful to us. So let's take a look at that idea. This one says use the factor theorem. So we are looking for values of a such that f of a is equal to 0. Now, unfortunately, there's no good way to do this. Well, there are really no great ways to do this, and it can get quite complicated. You're going to have to trust that, in general, for the purposes of this course and for math questions, you're generally going to be given options where you're going to get at least some reasonable answers. So this is a cubic, which means it potentially has up to 3 factors. So the first thing I'm going to do is, well, the easiest value I think is 0. So if I put a 0 in here, I get 0 cubed plus 4 times 0 plus 0. Oh, that's negative 6. Okay, so that one doesn't work. So let's try f of positive 1. Well, that's pretty easy. Let's go ahead and fill that in at least. 1 cubed is 1. 4 plus 4 times 1 is plus 4. Plus 1 minus 6. And so we ended up with 6 minus 6 is equal to 0. So that one worked. Now because that one worked, that means that, so this tells me that x minus 1 is a factor. That is what the factor theorem tells me. Hey, that's great that I got that on the second try. Well, what if it didn't work from there? Well, from there, then you might try f of negative 1, and then f of 2, f of negative 2. However you want to do is up to you. I would be methodical. I wouldn't do just random guesses. As we proceed through this, I'll introduce some other things that might help you out. For example, just off the top of my head, if, for example, I gave you a graph of this cubic, well, I might not put labels on the numbers here, but if you tried some numbers, you might get an idea of whether you are getting warmer or colder, getting closer or further away. The idea that here it's above the x-axis, here it's below. So there are some things that you can do to make your life a little bit easier here. Use some educated guesses, but there's still an element of randomness there. You don't know, you're just trusting that you're going to be able to find something. You have to make sure you're very careful with your arithmetic, otherwise you'll end up wasting your time as well. Okay, I'm sorry, I didn't finish this though, because we want to completely factor the function, which means we're going to make use of the skills we learned in our last lesson. So I'm going to do long division here. So x minus 1 divided by x cubed plus 4x squared plus x minus 6. And my first one is going to be an x squared times x, so that gives me an x cubed minus x squared. Remember, when you do long division, you subtract, so I end up with 5x squared plus x. And now I'm going to get plus 5x. 5x times x is 5x squared. And 5x times negative 1 is minus 5x. And then subtract that gives me 0, and this gives me 6x. And then plus 6. 6 times x is 6x. 6 times negative 1 is negative 6. I'm going to bring this one down. That becomes minus 6. And as you can see, those are the same. And I end up with a remainder of 0, which I should have gotten. So now, not to rush things, so just to give you an idea of what we got, because there's no remainder here, what we have now shown is that this original x cubed plus 4x squared plus x minus 6 can be written in a factored form of x minus 1 times this quadratic, x squared plus 5x plus 6. And that's a new skill that we've added for factoring. And from there, we also want to factor this quadratic. That's a pretty easy one. That's just a simple trinomial. So two numbers that multiply to give me 6 and add to give me 5 are 2 and 3. So this is x plus 2, x plus 3. And as you can see, I've now taken this cubic and I've written it and as a product of 3 factored. It is now fully factored. Okay, now rational numbers. Nothing new here, it's just reminding you. So when we talk about a rational number is something that's written as a fraction where both of the numbers in the numerator and denominator are integers. Typically, we only put our negatives in the numerator, at least after we're done simplifying, but technically both of them can be integers, and of course, no dividing by 0. So b cannot be 0. Now, we're talking about polynomials, we're talking about factoring polynomials, we're talking about roots of polynomials. So a rational root, as opposed to what I had here, which was an integer root or an integer factor. So a rational root is when you have a rational number as the root. So we would write this as x minus a over b, that's a rational number, but we could also write this in another way, which is this denominator goes here with the x, so bx minus a. So for example, if I said 3x minus 5 was one of my factors, then what is the root of that? Well, the way we do that is we solve it for 0, so we end up with 3x equals 5, or x equals 5 over 3. And that is the same as x minus 5 over 3 being a factor. So these two things have the same root. Now there's that extra factor of 3 we have to be careful of. If we wanted to say that these are exactly the same, and I showed this in a previous lesson as well, that's the same as saying 3x minus 5 is the same as factoring out a 3 and then having x minus 5/3 left over. That's another way to go directly to that answer. Now that's a bit of an aside, but it's an important one because we're not always going to have integer roots. Sometimes they're going to be fractions. And so what we're going to make use of is another idea, which is something called the rational roots test. Now this is going to be a lot to take in. To be honest with you, this is the tough part of this lesson. So if we have a polynomial written in this standard form, the way that you figure out your possible rational roots. So you know how I said back here, I said we would just keep trying until we found something that worked. Well, we can reduce our possibilities by using the rational roots test. And we still may end up with a lot more possibilities than you want to deal with, but it's better than nothing. It's better than having an infinite number of possibilities. Also, a little bit of a note, a little bit of a warning. It is possible to have what are known as irrational roots. For example, you might have something like x minus root 5, which would mean your root there is equal to the square root of 5. So this is a factor, x minus the square root of 5. So this is your root. Well, that's an irrational number, and the rational roots test is not going to discover that. So despite we're introducing all these new concepts, we still cannot guarantee that we're going to cover every possibility. And so as I say here, you might not be able to factor all polynomials. The only way you're going to be able to factor a polynomial that ends up with an answer like this would be if you got to something like a quadratic where you could use the general quadratic formula. Or I'm going to show you some other special patterns a little bit later in the unit, not in today's lesson though. Just a little joke there, don't worry about that, we'll talk about it in class. Okay, so here is an example that I've already worked out, just to show you that we've got a constant term here of -8. We actually don't care about the sign, so there's our constant term, so it's 8. And the leading coefficient of the highest order polynomial, or the highest order term, is 3. So the factors of 8, what numbers go into 8? 1 and 2 and 4 and 8 all divide into 8. The factors of 3 are 1 and 3. The rational root theorem tells me that the only possible roots are 1 or 1 over 1, 1 over 3, 1 over, oh that's it, 1 over 1, 1 over 3, 2 over 1 or 2 over 3, 4 over 1 or 4 over 3, 8 over 1 or 8 over 3. And I have to consider both the positive and negative possibilities there. As you can see, that is still a fairly large list. And then I take each one of these one at a time, and I use the factor theorem, and I start plugging them in. And I might have a bunch of failures. For example, +1 minus 1, +2 minus 2, +4 minus 4, and I wouldn't get my first success until -4, so I still would have had to go through 6 tries to get that. It can be a time-consuming process. It can be quite tedious. So let's go ahead and do that same thing here. So let's look at, now remember, it's the form of it is the factors of the constant term and the factors of the leading coefficient. Now you may think I've made this pretty awful, but it turns out the number 105 is not as bad as you might think. Because if we take the number 105 and we break it down into its different factors, well, 105 is the same as what? 105 is the same as 5 times 21. And then 21 is the same as 3 times 7. So from that one, my possible factors are going to be 1 or 3 or 5 or 7. And don't forget, it's always plus minus. And for 2, well, 2 is just 1 times 2. So that's an easy one. Okay, now this one doesn't ask you to do, it wants you to actually show that 2x plus 3 is a factor. So what does this tell me for all my possible roots? Now, I'm not going to write out the positives and the negatives here. I'm just going to say plus or minus. So it's plus or minus 1 over 1, which is just 1. 3 over 1, which is 3. 5 over 1, which is 5. 7 over 1, which is 7. Or 1 over 2. 3 over 2. 5 over 2. Or 7 over 2. So there's our first part. List all the possible rational roots. That's not so bad. Now, if I had to apply all of these to f of x, that would be pretty tough. But what about this one? I have 2x plus 3, which is the same as, if I factor out that 2, that's the same as x plus 3 over 2. So what is my k value going to be? If it's x plus 3 over 2, then my k value, or my root, is actually negative 3 over 2. When we talk about a root, that's the same as talking about a 0. What value of x makes this thing 0? Negative 3 over 2. And this question wants us to show that this is indeed a factor. So I'm now going to use the factor theorem. I'm going to take the negative 3 over 2 and I'm going to plug it in here. So I'm just going to rewrite that. 2x cubed plus 7x squared minus 64x. 2x cubed, I've already made a mistake. 2x cubed plus 7x squared minus 64x minus 105. That is f of x. So now I'm going to figure out what is f of negative 3 over 2. And this could get quite involved. 2 times negative 3 over 2, all cubed, plus 7 times negative 3 over 2, all squared, minus 64 times negative 3 over 2, minus 105. Okay, so let's go ahead and do this, and I'm not going to skip any steps here. Negative, so negative cubed is going to be a negative. 3 cubed is equal to 27. 2 cubed is equal to 8. Plus 7 times negative squared is a positive, so now it's positive. 3 squared is 9. 2 squared is 4. Minus 64. Actually, well, again, you know what? I'm not going to skip steps here. So I'm just going to rewrite this one. I could have evaluated this minus 105, but just to show you. Okay, so 2 goes into 2 once and it goes into 8 4 times. And that gives me a total of negative 27 over 4. 7 doesn't go into 4, so this one just gives me plus 63 over 4. 7 times 9 is 63 over 4. 2 goes into 2 once and goes into 64 32 times. So this gives me negative 32 times negative 3, which is equal to positive 96, minus 105. Now, since I've already got things working out with the fractions here, I might as well go ahead and evaluate this first. So that works out to be 36 over 4, positive 36 over 4 here. And then 96 minus 105 is equal to subtract 9. Just make sure I've got that right. Yes. Okay, now 4 actually goes into 36. 4 goes into 4 once, and it goes into 36 9 times. And I end up with 9 minus 9, which is equal to 0, which is what I was trying to show in the first place. I wanted to show that 2x plus 3 is a factor, and I showed that using the factor theorem. And that's it. Well, I say that's it. I feel like that was a lot. That's a lesson that you're probably going to want to go back, pause it, take a look at things, take a look at the notes in class and compare. Take your time and really make sure that you give this homework your full attention, because the stuff that I did there was not easy. It's certainly not easy the first time that you see it.